Welcome to Modular Learning Channel, Networking Technology. My name is Learning-WHu. Today, we will talk about spanning tree protocol. Enterprise network has redundant links between switches to ensure reliability. The redundant path creates physical loops, like we see here. The network loop causes instability of MAC address table. For example, PC1 center frame, the access layer switch will create a MAC address table entry to associate PC1 with port 6. In the meantime, the switch forwarded the frame out both uplinks. Since it's a loop, the frame will coming back on different ports. Then the switch will update the MAC address table entry for PC1. Then short after, the frame will loop on different ports. Access layer switch will update the MAC address table again, causing instability for MAC address table entry. Another issue is that if PC1 send the frame to PC2, access layer switch will send the frame out both uplinks. As a result, PC2 will receive duplicate frames from PC1. This example showing a network loop generates broadcast store. PC1 sends one broadcast frame. Switch receives it, forwarded out all ports except the source ports, then produce 3 broadcast frame. Those 3 frames forward to the other 3 switches. Those switch will forward the broadcast frame out of all ports again, that produce the orange broadcast frame. Then when the orange broadcast frame send again, the switch receives the number 3 broadcast frame, will forward it out, generate the number 4 broadcast frame, the green one. So we can see a single broadcast frame from the PC after few forwarding produces 12 green broadcast frame. This is a broadcast store. Imagine if there are more PCs, those PC also send broadcast frame. The broadcast frame at layer 2 does not have TTL, time to leave. So once it introduced into the network loop, it will be circulated forever. Then the broadcast traffic will saturate the network bandwidth, eventually crash the network. Spanning tree protocol 802.1d creates a loop-free logical path on switched network by blocking a port. So PC1 will use left link, talk to PC2. If the left link failed, the access layer switch will open the blocked port to enable alternative path for communication. Then the spanning tree use the BPDU as a message. So all spanning tree switches exchange BPDUs every 2 seconds on every active port. The information in the BPDU includes root bridge ID, root path cost, sender bridge ID, and the sender port ID. So the bridge ID, you can see, is a bridge priority followed by MAC address. The 2 bytes bridge priority actually use the first 4 bits as priority number. Then the following 12 bits representing the VLAN ID, it's called extend system ID, then followed by MAC address. So the priority number is configurable. That's how we give the bridge or switch a specific priority. So the switch with the lowest bridge ID becomes the root bridge. Another important information in the BPDU is the root path cost. Root path cost actually is accumulated path cost from the receiving switch to the root bridge. So the port cost is the path cost. That is determined by port speed. You can see a 1 gig port. The cost of the link would be 4. A fast Ethernet link, the cost is 19. So the switch will use this to calculate how far the root bridge is from the receiving switch. Let's look at the spanning tree operation. The spanning tree uses the 4-step process. Step 1, all the spanning tree switches will elect a root bridge based on the bridge ID. Second step, all the long root bridge will elect a root port. That is the port closest to the root bridge. Step 3, the switch will elect designated ports. Then finally, step 4, elect the blocked port. Then here we'll use a 3-switch topology as example, and we can see the priority is given along with the MAC address. Combine bridge priority and the MAC address, that is the bridge ID. After exchanging the BPDUs, every switch receives the bridge ID from other switches. So the switch will be able to compare which switch has the lowest bridge ID. In this case, let's compare. So first, compare the priority. They are all the same, which is the default value, 32,769. There is a tie. The tiebreaker would be the MAC address, which is the second part of the bridge ID. So we can see switch 1, MAC address is 00B. Switch 3 is 00A. Switch 2 is 000. Switch 2 has the lowest bridge ID because the MAC address. After root bridge is elected, other non-root bridge, switch 1 and 3, will elect a root port. Root port is the port closest to the root bridge. And so, for example, switch 3 has 2 ports to the root bridge. Port 2 is only 1 hop. The cost of this link is fast Ethernet, cost equal to 19. And port 1 having a longer journey to the root, the total path cost from switch 3 to root via port 1 is 38. So obviously, port 2 has lower path cost to the root. So port 2 becomes the root port. This is the decision sequence. The switch uses the path cost to determine which port is going to be the root port. And the same reason, switch 1 use port 5 as root port because the path cost to the root is lower than port 6. Okay, the next step, the 2 switches, switch 1, switch 2, is going to elect a designated port over this link. Designated port means the port will control the traffic over this segment. So it's going to first compare Switch 3 says, oh, I have a root path cost of 19 to the root. Then switch 1 says the same. I can reach root with the cost of 19, so there is a tie. The two switches will compare the second criteria, the lowest sender bridge ID. So switch 3 send the BPDU over this link. The sender bridge ID is the priority and the MAC address 00A. Switch 1 send BPDU with the sender bridge ID, same priority with the MAC address 00B. So switch 3 has lower sender bridge ID. Switch 3 wins. The competition becomes the designated port on port 1 over this link. So the port on the switch 3 becomes the designated port over this link. Then the other side of this link will be blocked to break the loop. And this is how spanning tree make the calculation, follow the decision sequence. Okay, so this example has two switches interconnected with two links. This is a loop. And the spanning tree switch will perform the spanning tree operation. First, elect the root based on the root bridge. Then compare the root bridge between these two switches. We can see the top one has priority 32.769. The bottom one has priority 24.577. Obviously, the bottom switch has a lower bridge ID because of the lower priority. And that makes switch 4 the root. This is the first step. Root bridge is elected. So all the ports on the root bridge will be designated automatically. Designated means all forwarding and receiving operational. After that, the non-root bridge will elect a root port. And the decision sequence is compare the path cost. So the switch 3 has two links, same speed to the root bridge. So obviously the path cost to the root are equal among these two links. So there is a tie for the first decision criteria. It will use the second decision factor in the sequence. So lowest sender bridge ID. The sender bridge ID is the root bridge. So both links receive the BPDU with the same sender, switch 4. Again, there's another tie. Tiebreaker for the second criteria would be the last one. Use the lowest sender port ID. So now the sender port ID lower one is F05. The non-root bridge switch 3 determined port 2 will be the root port because the sender port ID F05 is lower than the other port. Then obviously switch 3 will block F01 to break the loop. And this produces a loop-free topology. Let's verify the spanning tree operation in packet tracer. We have 3 switches form a redundant network. The scenario is PC connected to access layer switch and the 2 distribution layer switches. The orange in the packet tracer indicates this port is in spanning tree blocking state. The blocked port is always on the far side from the root bridge. So let's use the spanning tree operation principle. Verify the spanning tree operation here in the packet tracer. So if we take a look to show spanning tree, and this access layer switch shows this bridge is a root bridge, and you can see the bridge ID is the same as root bridge ID, so that confirm this is the root bridge. The MAC address of the root bridge is 0001. Default priority is always 32.769 for VLAN1. And let's check the distribution layer switch that has the port blocked. Show spanning tree shows the root bridge is 0001, which is ALS layer switch. The bridge ID for DLS1 is 00E0. So that MAC address obviously is higher than the root. And the priorities are the same. All switches are having default priority. So let's check the third one. DLS2. Okay, we can see the root bridge is pointing to the same ALS1. The current bridge ID is 003. So we saw ALS1 becomes root bridge because it has the lowest MAC address when all the switches are having the same priority value. The MAC address is the tiebreaker. Okay, so in the real world scenario, we would prefer to configure distribution layer switch as the root. So the port blocked would be on the access layer switch. So let's see how do we do that. Simply go to DLS1. We can just tell spanning tree VLAN1. Currently, we are looking at VLAN1 only question mark. You can see root. And then you can configure this DLS1 as primary root or secondary root. And so I just configure it as primary. And this is the spanning tree configuration you normally need to do. Configure a root bridge. That should be the distribution layer switch. Then the second distribution layer switch would normally be configured as spanning tree VLAN1 root secondary. Then act as the backup. If DLS1 done, DLS2 is still a root. Okay, after this configuration, we can see the port used to be blocked. Now it's forwarding, and the port on the other side here is blocked. But if you want to configure DLS2 as a secondary, the blocking port will shift to the access layer. Let's try it. So go to DLS2, configure spanning tree VLAN1 root secondary. Okay, right after this, let's check to show spanning tree. And we see the port 3 is transition to listening. Port 3 is this port. And port 1 is root port connected to the root bridge. The root bridge right now is 00E now instead of 0001. So it's this guy. And if we keep watching, now the port is becoming forwarding designated ports. So these two switches are competing the control of this link. Who will becoming the designated port? It will compare the path cost first. For the path cost, both the switch ALS and the DLS2 are having the same root path cost to the root bridge. And so it will move on to the second decision sequence that will compare the sender bridge ID. Both of them send the BPDU over this link. Who has the lower sender bridge ID wins the competition, becomes the designated port. Okay, the bridge ID on DLS2 is having the lower priority, 28,673, because we configured it as the secondary route that automatically lower the priority value. And look at the ALS, the bridge ID priority on ALS is higher, 32,769. So that's why DLS2 becoming the designated port over this link. Then the other side on ALS is blocked. Blocking ports is on the access layer switch. This is the normal spanning tree configuration. You would configure one distribution layer switch as root primary. The second distribution layer switch is the root secondary. And the blocking port is on the access layer. So if the current forwarding path failed, the blocked port will be open and the secondary link will be enabled. So if we take a look, if we delete this link, delete this, you will see the link will be open after 30 to 50 seconds because the spanning tree ports needs to go through blocking state, listening state, learning state, and forwarding. Now, the three ports, all ports are forwarding. Spanning tree actually has timers to control the convergence time. So we already know the spanning tree switches exchanging the BPDUs every 2 seconds. That is also considered as hello. When the topology changes, spanning tree switch will transition the spanning tree ports from blocking state, stay there for 20 seconds, waiting to receive the BPDUs to do the spanning tree calculation, then transition to listening. When the ports is in blocking, it doesn't send the BPDU, it only receives BPDU. When it transitions to listening, the port will be able to receive and transmitting the BPDU. Then it stays there for 15 seconds, then gets into learning stage. At this stage, the port will be learning the MAC address from the attached PCs and populate the MAC address table. Stay there for 15 seconds, then the port is fully functioning, moved into the forwarding state. So we can see it takes the switch about 50 seconds to transition the spanning tree port from blocking to forwarding. That's why when you plug a cable to the switch port, it takes about 50 seconds before you can use the port. You will see the LED on the switch port starting from amber. It takes about 30 to 50 seconds to change the LED color from amber to green. That is fully operational. Next video, I will demonstrate the spanning tree variations and show you how to configure different versions of spanning tree. Okay, see you next time.